Hey, physics class. We're going to do a couple problems today. Just Ross and Acker. Remember to smash that like button and subscribe. So here's our first problem. You want to move a 250 kilogram chest freezer into the corner of the basement. You put gliders with a non-stick surface under the feet of the freezer. If you push with a force of 80 newtons and the freezer accelerates with 0.08 meters per second squared, what is the coefficient of kinetic friction of the non-stick surface on the cement floor? So you can see over here our coefficient of kinetic friction is equal. So our force of friction is equal to our coefficient of kinetic friction times the normal force. Now, they're asking for the coefficient of kinetic friction, so I'm going to put a question mark over that because that is what we're looking for. They give us the mass of our chest freezer, so we can find the force of normal by taking 250 kilograms times 9.8, because we know that if gravity is pushing down, the force of normal will be pushing back up with the same amount of force. So I can enter into my calculator 250 times 9.8, and I know that we have 2,450 newtons of normal force. So since I'm looking for this, then the last thing I need to find is the force of friction. It tells us that we are pushing the freezer with a force of 80 newtons. And obviously we're going to have some force of friction pushing back against that movement. We know that if I were to draw my net force, which my net force in the x direction would be equal to the positive 80 newtons I have minus my force of friction. So my net force gives me an acceleration equal to 0.08 meters per second squared, and we found that right up here. So if I know that force is equal to mass times acceleration, and I know my mass to be 250 kilograms, I can take 0.08 times 250 and find out that I have a net force of 20 newtons. So 80 newtons minus my force of friction is going to give me a net force of 20 newtons. And with a little simple math, I can find out that my force of friction is 60 newtons. So I can plug in 60 newtons right here. 60 newtons is going to be equal to my coefficient of friction times the 2,450 newtons we found earlier. So I'm going to take 60 divided by 2,450. And I'm going to find out that I have a coefficient of friction of 0.02, and we'll round that to 5. Okay, now is problem number 1. Alright, here is our second and slightly more complicated problem. So, in this problem we have a system that's in equilibrium. We're going to calculate the force of friction acting on the block A. So right here we have our block A. We're going to have a force of friction on block A. Obviously that force of friction is going to be caused by our force this way, and we'll just call that like the force of the rope on A, because this rope is going to pull on A this way. We have the rest of the rope, which is connected to the ceiling, pulling on A and pulling on B. B is going to have a force acting on it, but since it's not touching anything else, that force is just going to be the force of gravity, and then of course the force of the rope pulling up on B. So we'll call it force of rope on B. Lastly, we have our force at this angle this way, which is pulling us up towards the ceiling. They tell us that that angle is 33 degrees, and they give us the max, or the masses of our blocks. So we need to add a couple forces to A before we can solve. We know that A is going to have some force of gravity acting on it, pushing down into whatever this surface is. And that surface is going to be pushing back up with a force that we call our normal force. Now, the reason we need to solve for our normal force is because they're asking for our force of friction. So just like in the last problem, we're going to need to take the force of friction and multiply it. Or we know force of friction is equal to the coefficient of friction times our force of normal. Just like last problem, they ask for calculate the force of friction. They do not give us a coefficient of friction. So our normal equation is not going to be that helpful to us. So what we're going to do is we're going to break these down. I know that these two forces are balanced, so they're going to cancel out. Since we can't use our normal equation that we would use because we don't have this variable, we're going to have to use a different equation. Thankfully, in our last chapter, we learned Newton's third law that says the opposite of the force of R on A is going to be the force of A on B. So if we can figure out what this force is, this force will be equal and just in the opposite direction. We know that since this system is in equilibrium, A is going to equal 0 because the net force on this entire system is going to equal 0. The easiest way for us to solve this problem is going to be to divide our components into two types of components. We're going to have our x components and our y components. Now, A, we talked about already. The two y components in A cancel out. So we are going to have one component in A, and that is going to be the force of friction is going to be going this way. So we'll call our net force on this entire system Rx. And Rx has to be equal to 0 because otherwise we'd be moving one of these two ways. And that has to be equal to the force of friction minus, and then we'll call this guy, I don't know what we can call this guy. We'll call this guy A. No, we don't want to call him A because that's A. We'll call him C. So this line right here, I'm going to call C. So minus, and C is going to have two components, so minus C of x. So the component of C that is pulling in the x direction has to be equal to our force of friction. Likewise, our resultant of this is going to have a y component. That y component tells us that the force of gravity, F of g on B, is going to be equal to 1 is going to be equal to 0 because we're in equilibrium, and it is going to be equal to this guy minus, and then we'll call him C of y. Now, this would be great time to use our AX is equal to A cosine theta and AY is equal to A sine theta, except we have no magnitude for C. So we're going to do a little arithmetic to figure it out. So I am given a mass on my block B. So I can take 4.3 and I can multiply it by 9.8 and 4.3 times 9.8 gives me 42.1. And 42.1 has to be equal to this vector right here, which would be my C of y. Now, this is where we're going to have a little fun and do some trig. So, this equation that we said we couldn't use for a of y, where I have a of y is equal to a sine theta. We couldn't use it to break a into the two parts, so we had to find cy a different way. But now that we have cy, we can use that equation, and we can say cy is equal to c sine, and our theta is right here, measured from the positive x-axis, of 33. So, since we know cy has to be equal to 42.1 for this to be an equilibrium, we can say that 42.1 is equal to c times sine of 33. If I plug sine of 33 into my calculator, I get 0.5, and we'll run that to 0.55. I can take 42.1 divided by 0.55 and find out that my magnitude of c has to be 76.5. Now that we have c, we can use our opposite equation over here. We can use cx is equal to c, which we just found was 76.5. And this time we'll do cosine, so that we can find our x component of 33. So if I take 76.5 times the cosine of 33, I find out that my c of x is equal to 64.2, which means that in order for this to be an equilibrium, if I have 64.2 newtons this way, I must have 64.2 newtons this way for friction. So I found out that the force of friction that has to be acting on A is 64.2 newtons. I hope these two problems helped you guys out. I know that second one got a little bit confusing and is a much more difficult problem. Go ahead and talk to me in class if you have any other questions. Thanks for watching.